Right, ladies and gentlemen, welcome to this demo lesson. Today we're discussing one of the computational questions in Year 12 chemistry curriculum. Now, the reason why I have chosen this question to do this example is that even if it's a multiple choice question, it's not easy. It's looking at quite a big range of critical concepts highlighted in the Year 12 chemistry curriculum. And then if you look at this question, it's giving us something called Ka, it's giving us a chemical reaction with a double arrow in between, it's giving us some molar concentration. So to solve this question successfully, we need to have very good understanding of chemical equilibrium, especially how to use the equilibrium constant, which is Ka, for problem solving. Alright, so we need equilibrium constant. And how to mathematically use this constant to solve for the unknown concentrations. The second types of critical concepts are looking at molar ratio. Sometimes we rely on the molar ratio between compounds to look for the unknown concentrations, and also because the question has given us something called concentration, addressed with m as a unit, so we need to have a pretty good understanding of molar concentration as well. Now, if you guys can solve this question without my help, that means you have already got perfect understandings of these concepts. You should be proud of yourself. All right? So back to this question. We are having a table looking at the chemical property of ammonium ion, NH4+, one single platinum charge. The Ka given is 5.6 times 10 to the power negative 10. And then also given by the question, we are having a chemical reaction. So to help with my further explanation, to write the equation on the board. So we are having ammonium ion, we're having water, because the reaction describes what happens once we have this compound in water solution. And then we are having a double arrow showing its equilibrium, so we have to consider the rate of forward reaction, the rate of the backward reaction as well. And then we have this ammonia gas in aqueous solution. We're having this hydrogen ion as well. Now this equation is showing that the ammonia ion has ability to play as an acid because it has the ability to donate a proton, making this a hydronium ion in water. But considering the Ka, which is a pretty small number, describing how much the forward reaction can happen, this acid is pretty weak acid. Alright? And then apparently we're relying on Ka for further problem solving. So I'm going to write the fraction for the Ka, for the equilibrium constant. The Ka equals. Now just recall what makes this fraction. We have something on top, something at the bottom. Because the Ka is addressing the forward reaction, so we have products on top of the fraction. Now in this case we're having two products. We're having ammonia gas and we are having hydrogen ion. And because Ka is a mathematical concept, we have to have these symbols used in the correct way. The square brackets represent concentrations. Now at the bottom of fraction, we need to have the reactants. Now in this case, I have two reactants as well. We have the ammonium ion, which has to be there. And then there comes into decision making. Do we include water in this case as well? Now please be aware that water in the reaction is having an L by the side, which means water in this case is playing as a liquid. Now we assume that the water in this case is pure water, which means the concentration of water is 1. Now in that case, there's no need to include water in the equilibrium constant. Just to remind everyone by the side, there are a few cases we need to include water in the equilibrium constant. And one of them being when water is playing as a gas and is having all the compounds in their gas form. Okay? In that case, water must be included. In this case, water is not. All right. Now, so basically, for problem solving, we need to find relative numbers to be substituted into this fraction. Apparently, we know the Ka, which is 5.6 given by the question. All right, we know that. For ammonia gas in the aqueous solution, we have no idea what the concentration is. Now, for the hydrogen ions concentration, the question is asking for that, right? It says the hydrogen ion of whatever solution is closest to, so I put a question mark on top of it. And then the concentration of ammonium ion is not given either, so there's no way to find it from the information given by the question straight away. So we have to look at the information that we have not referred to yet. Now the question says 0.2 m molar concentration ammonium chloride solution. So now we need to look at how to use this number to help us find these two figures. The concentration of ammonium chloride is 0.2 mole per liter. And then considering ammonium chloride is a pretty strong electrolyte, now at this stage, if you have no idea what strong electrolytes are, electrolytes are those compounds, once they're placed in water solution, quickly they will release ions. So if you look at this ammonium chloride, once it's in water, it quickly releases the ammonium ion and then the chlorine ion. And then because it's a strong electrolyte, the forward reaction is happening at a pretty high rate. We would simply use a single arrow to show the comparison between the forward and backward, right? There's no need to use double arrow at this stage because it's a strong electrolyte. All right? And then if you look at the molar ratio between these three compounds, in every 1 mole of ammonium chloride, it would release 1 mole of ammonium ion, which means if the concentration of ammonium chloride is 0.2 mole per liter, the concentration of the ammonium ion, it should be 0.2 mole per liter as well. All right, so this is something we have found by looking at the relation between the ammonium ion and the ammonium chloride. All right, now up to this stage, we have just found the concentration of the ammonium ion, right? But have a look at the ammonia gas in the aqueous solution. How do we find the concentration of that? There's no way, right? Now don't panic. Now go back to the original equation. Once we are having ammonium ion in water, it will quickly release ammonia gas and the hydrogen ion. And then for every single one ammonium ion, we will have 1 ammonia gas and 1 hydrogen ion, which means these two guys must be of the same amount. Right, these two products are made at the same time, so their concentration should be the same. Now, once up to this stage, we can put something into the equation. Now, I'm putting a question mark on top of the ammonia gas as well. And then we have the Ka, 5.6 times 10 to the power of negative 10. And then we are having at the bottom, we have ammonium ions concentration, which is 0.2. And then we're having two question marks on top of fraction. Now these two question marks are of the same quantity, so actually I can make them both x, which is a generic symbol for unknown combinations, right? So I'm having x times by the other x. Alright, now so far probably you have noticed that the only purpose now at this stage is to mathematically solve the equation for x. Now, how do we do that? We multiply both sides by 0.2 to cancel out the denominator, and then we would have 0.2 times 5.6 times by 10 to the power of negative 10 equals x squared. But be careful, okay, we're looking for the value of x, we're not looking for the value of x squared. So, once you use a calculator to find this value, you need to reverse the operation by taking square root on both sides. Now, finally, this x would be a value, which is the square root of the number on the left, and then I'm leaving you guys to figure out what this number actually is, okay? And then you simply find what it is from the four options, and you will have the right